Part 2 of Unit 7 is about the basic gas laws. Hopefully this is all review from Chem 1. The first gas law we're going to talk about is Boyles Law. It says that when pressure increases, volume decreases, or when volume increases, pressure decreases. This is called an inverse relationship, and it takes place as long as the temperature is held constant. In the formula for Boyles Law, P1 times V1 equals P2 times V2. So pressure times volume equals pressure times volume. But we'll solve an example problem using Boyles Law. A 3.5 liter oxygen gas container has a pressure of 133.5 kilopascals. Calculate the pressure if the volume of the container was tripled. So the 1 and the 2 subscripts in our formula, they tell us the difference between the initial and changed states. So we'll put the initial conditions all together on one side. So initially, our pressure was 133.5 kilopascals. And our initial volume was 3.5 liters. Now something is changing. We're tripling the volume of the container, so we have to solve for the new pressure. So we're solving for P2. And we're going to plug in that tripled volume term over here. 3.5 times 3, that's 10.5. So to solve for P2, all we have to do is divide this side by 10.5 liters. So you plug that into your calculator and you get that P2 is equal to 44.5 kilopascals. Easy, right? The next basic gas law is Charles' law. It says that when the volume of a gas increases, the temperature of the gas also increases. When the temperature is decreased, the volume of the gas is going to decrease as long as the pressure is constant. This is a direct relationship, and it's got the formula of V1 over T1 is equal to V2 over T2. It works just like Boyles' Law does. We got our initial and changed conditions, and we're going to end up solving for the unknown. So our example, a balloon inflated in a room at 24 Celsius has a volume of 4 liters. Balloon is then heated to 58 degrees Celsius. What is the new volume of the balloon? Well, our initial volume was 4 liters, and our initial temperature was 24 Celsius. The balloon was heated to 58 degrees Celsius, so we changed the temperature, and we need to solve for the new volume, V2. So once you do your algebra and solve this, you can cross multiply, or the way I would do it, you just do 4 divided by 24, then multiply by 58. It all works out the same, but V2 is going to be equal to 9.67 liters. That's Charles' Law. Also easy. The third basic gas law is Gay-Lussac's law. As temperature of an enclosed gas increases, the pressure increases, and as pressure decreases, so does temperature. And this happens as long as the volume is constant. This is also a direct relationship, and the formula for Gay-Lussac's law is P1 over T1 equals P2 over T2, and it works just the same as the other ones do. So in our example, the gas in a used aerosol can is at a pressure of 103 kilopascals at 25 degrees Celsius. If the can is heated, what will the pressure be when it reaches 928 degrees Celsius? Our initial pressure is 103 kilopascals, and our initial temperature is 25 degrees Celsius. Now we change the temperature. We increase it to 928 degrees Celsius, and we need to find the new pressure. When you end up solving this, you get that P2 is equal to 3,823.4 kilopascals. So I bet that aerosol can likely exploded before it reached 928 degrees Celsius. The two examples we used Celsius as our temperature unit. It could also work the same way with Kelvin. Just make sure you've got the same unit on both sides of your equation. We can combine all three of those basic gas laws into one equation. It's called the combined gas law. PV over T is equal to PV over T. That's the combined gas law. If something is held constant, it's canceled out, and the equation becomes one of the three basic equations. So if something takes place in a container with constant volume, the volume terms would go away, and we'd be left with Gay-Lussac's law. Just pay attention to what the question is asking for, identify the unknown, and solve for it. Those basic gas laws are really easy to use. The next gas law is Dalton's law of partial pressures, and I still find it hard to believe that Dalton got something else named after him for figuring out something so simple, but the law of partial pressures says that the total pressure in a container is equal to the sum of the pressures of all the individual gases in that container. P1 plus P2 plus P3, however many different gases there are, each gas has its own individual pressure, and the total pressure in that container is the sum of all of those gas pressures. It's brilliant, I know. Let's work an example for it. The pressure of a mixed nitrogen, carbon dioxide, and oxygen container is 150 kilopascals. What is the partial pressure of oxygen if the pressures of the nitrogen and carbon dioxide are 124 kilopascals respectively? Well, our total pressure, they told us, is 150. I'll back up. So the total pressure is going to be equal to the pressure of the nitrogen plus the pressure of the carbon dioxide plus the pressure of the oxygen. Total pressure is 150. The pressure of the nitrogen is 100 kilopascals. The pressure of the carbon dioxide is 24. And we would be solving for the pressure of oxygen. So 150 minus 124, that's pretty easy, right? Our total pressure, or not total pressure, the partial pressure of oxygen is going to be 26 kilopascals. Your question for this section: a gas is initially at a volume of 17 liters, 2.3 atmospheres pressure, and 299 kelvins. If the pressure is raised to 350 kelvins and the pressure is dropped to 1.5 atmospheres, what will the new volume of the gas be?